So yes, the next topic that we are going to talk about is the wetting and the contact angle. Yet again a very important topic from your exam point of view. Students, you need to understand what is the concept behind the contact angle and how it is related to the wetting. Alright, so firstly we are going to talk about what actually this contact angle means. Right? So students, so we have to first define the contact angle. Actually, the contact angle basically explains how well or how poorly a liquid is going to spread over the surface. Okay, so it basically explains how well a liquid is going to just a second, I'm going to just write what I'm saying so that you understand it even better. Yes, so wetting and contact angle, right? So contact angle is nothing but it explains, contact angle explains how well or how poorly a liquid is going to spread over the surface. Alright, so it indicates how a liquid basically is going to interact with a solid surface. Okay, so when the liquid droplet, suppose I'll just show you with an example here. You have to understand the angle values also. Suppose this is a solid surface, okay, and here it is a liquid droplet. So this is the contact angle as indicated here. This right here, this theta, this indicates the contact angle. Okay, so the angle of contact between what? Between the liquid droplet and the surface. Okay students, so now as you must know that lower the contact angle, lower the contact angle, higher will be the wettability. Higher is the wettability. So in generalized terms, we can say that the contact angle is inversely proportional to the wettability. Okay students, so now we have to see what are the different angles that a contact angle can possess for having a perfect wettability like condition. So suppose this is a complete spherical droplet. Here the angle is approximately 180 degrees. This will indicate non-wetting conditions. This will indicate the non-wetting conditions. This is a very important thing from your exam point of view. Kindly note this down that yes, if the angle will be around 180 degrees, then there will be no wetting that will take place. Suppose here the angle is here, the angle is 0 degrees. Then there will be complete wetting. There will be complete wetting. Okay students, now which means suppose this is the contact angle that we had been talking about. If this contact angle, just a second, I'll just make it again. If this contact angle is less than 90 degree, if this contact angle is less than 90 degrees, then only wetting will take place. If it is more than 90 degrees, then there will be no wetting at all. Another thing is, if the theta will be, if the contact angle will be 0, there will be complete wetting. So you must know that the contact angle is inversely proportional to the wettability. Higher the contact angle, lower will be the wettability, or lower the contact angle, higher is the wettability. So wettability is what? Wettability is the ability of the liquid to maintain its contact with the solid surface. You must understand this, that the wettability is ability of the liquid to maintain contact with the solid surface. Okay students, then wettability, that will be inversely proportional to the contact angle. This is a very important topic from your exam point of view. Here I have just mentioned what I have just told you. What is contact angle? It is the angle between the liquid droplet and the surface over which it is spreading, right? So it indicates the efficiency of the wetting agent that have been used. So as I have mentioned, contact angle is inversely proportional to the wettability. Okay students, it generally lies between the 0 to 180 degrees. I have already mentioned, if the angle of contact will be 0, there will be complete wetting. If it will be greater than 90 or 180, there will be no wetting at all. Here it is mentioned 0 means complete wetting. Okay students, and 180 means insignificant wetting. Very important from your exam point of view. Right, now here is another question that has been asked a lot of times, that how do you measure the efficiency of wetting agent? Please see that a direct question can be asked on the Drave's test. Very important students, please mark it, that Drave's test is used for testing out the efficiency of the wetting agent. Okay students, now coming to our next topic, that is the surfactants or the surface active agents. Now as the name suggests, surface active agents. So these surface active agents or the surfactant, hereby I am writing surface active agents. These contain both hydrophilic parts. And the lipophilic parts. Right? So these surfactants, they are known to bear a hydrophilic part as well as a not hydrophilic, or the hydrophobic or the lipophilic part. As you can see, there is a polar part, polar head portion, which is hydrophilic, and there is the tail portion, which is the lipophilic part. Okay students, so what happens when a surface active agent is added? You must understand, when we add the surface active agent, I am just writing it down, when we add the surface active agent, I am marking it with SA, it is the surface active agent. When we add it to the air liquid interface, how do we represent this interface? I am just drawing it right here. This is the air portion and this is the liquid portion. What happens when we add the surface active agents to the air liquid interface? The surface active agents tend to align like this, in which the polar heads are towards the hydrophilic portion is towards the water and the hydrophobic tails are away from the water. Alright students, you must understand, when upon adding the surface active agents to the air liquid interface, the surfactants are known to orient themselves in such a way that the polar head is towards the water, due to which they are the hydrophilic part, and the non-polar part, that is the tail part, is away from the water, that is towards the air, which is the lipophilic part. So this orientation is tend to expand at the interface, and this orientation tends to lower down the surface tension. Very important point. This, whenever the surfactants orient this way, they tend to lower down the surface tension. Now as you add more and more surfactants, as you try to add more and more surfactants, what are you doing? You are saturating the air liquid interface, which will further lower the interfacial tension. Upon further adding the surface active agents, there will be a point where complete saturation of the interface will take place. Beyond this saturation point, even if you try to add more surfactant, it will move into the bulk and will tend to form the micelles at the concentration known as critical micelle concentration. As I'll explain it again, I have said that upon adding the surface active agents to the air liquid interface, what will happen? The surface active agents usually orient themselves in such a way that the polar head groups will be moved towards the water, and the non-polar tails, what will happen? They will move away from the liquid in the because they are the non-polar and lipophilic part. Okay students, now this orientation will tend to reduce the surface tension, and if you add more and more surfactants to it, it is going to saturate this air liquid interface, and till then the surfactants addition of more quantity of surfactant will make them move into the bulk of the solution, which will cause micelles to form, and these micelles at a concentration that will be formed is known as critical micelle concentration. So after the saturation, if you add more SSA, more surface active agents, it is going to form micelles at a concentration known as critical micelle concentration. Very, very important concept students. You must understand this point, that beyond the saturation point, the excess surfactant is going to move into the bulk and is going to form a micelle. Okay students, I am just going to draw what I just mentioned. Yeah, so this is the air and liquid interface. The surfactants are saturating the surface, where the polar heads are the hydrophilic portions is towards the liquid, and the hydrophobic tails, this is the non-polar part, which is the lipophilic part, and this is the polar head part. Upon subsequent addition, ultimately they are going to move into the bulk and form micelles. Okay students, so another major thing that you should know, that what are the classification of the surfactants. Very, very important students, classification of surfactants. Surfactants are generally classified into two groups. You should know that they can be categorized into the ionic part and the non-ionic parts, right? The ionic part, what does the name suggest? That it contains some amount of charge. Either it can be positive charge or can be negative, or it can have a no charge, which is termed as a non-ionic surfactant. Okay students, so you should know we are discussing the important topic, that is the classification of surfactants. I have mentioned it as the ionic surfactant, okay, or the non-ionic surfactant. This is the basic classification. Ionic surfactant, as the names indicates, that the hydrophilic or the polar part, what does it contain? The hydrophilic polar part contains some amount of charge. This charge can be the positive charge, the negative charge, or the no charge, or no, we have it is the Zwitter ionic. Yes, the correct is the Zwitter ionic form. While in the case of non-ionic, the hydrophilic part contains absolutely no charge. Okay students, this is termed as the ionic, the other one is termed as the non-ionic. So based on this classification, the ionic surfactant is further classified into the anionic surfactant, into the cationic surfactant, and into the Zwitter ionic forms. All these three forms comes under the classification of the ionic surfactant. As the name suggests, the ionic surfactant which indicates that the hydrophilic part is attached to with the negative charge. The hydrophilic portion is attached to the negative charge. In case of cationic portion, the hydrophilic part is attached with the positive charge. But in case of zwitterionic form, what happens? In zwitterionic form, the hydrophilic part, the polar part, is attached to both positive and negative charges. So before going into the depth of the important examples, I am making just a representation of how these surfactants actually look. I have mentioned there is one ionic part. Before that also I have mentioned there is a head part, that is the polar part. Just a second, just a second, just a second. So yes, now I am going to show how these are actually represented. So here, suppose this is the polar head part, this is the non-polar tail part. Okay students, so now as you can see there is no charge that I have mentioned. So this comes into the category of non-ionic surfactants. Okay, and next it is indicated the hydrophilic part is attached to some negative group. So it comes under the classification of anionic surfactant. Okay, similarly, suppose this hydrophilic part is connected to the positive charge group. Now it is a cationic surfactant. Okay, so if it is attached to both the parts, the negative as well as the positive part, then it is termed as the zwitterionic form. You must know that these zwitterionic surfactants are actually affected by the pH also. So if the pH is higher, they will be categorized as the ionic ones. If the pH is lower, they will be termed as the cationic ones. So as per the pH also, they tend to change their behaviors. Okay students, so this was about the basics of what are the surfactants and what are the classification. I have mentioned the classification as the ionic and non-ionic. Among the ionic part is the your hydrophilic part if attached to the negative charge, then it is the anionic one. If it's positive, it's the cationic, and if it's zwitterionic, there will be both the parts, the positives and the negatives. Now we will understand what are the examples that we must know before moving ahead. In the anionic part, you should know in the anionic part, the example is mostly the soaps of alkali. Mainly example includes the soaps of alkalis, including the sodium oleate, as well as the most used surfactant, that is the sodium lauryl sulfate, that is the SLS. These are the most important examples. Directly question can be asked, soaps of alkalis or generally SLS, which is the most commonly used surfactant. Next, for the cationic part, the example is the quaternary ammonium salts. The example is the quaternary ammonium salts. Right, for the non-ionic part, for the non-ionic surfactant, the important example can be into two parts where the separate questions can be asked. They are classified into the spans or the twins. Very important students, very important. Please mark it important, because the spans are categorized as the sorbitan esters. The span is categorized as the sorbitan esters. Direct question is asked. Wherever I mentioned the direct question is asked, it has been like asking about it, like if in the 5 years, last 5-10 years, this question has been on the repeat mode. Okay students, so the span is the includes the sorbitan esters, whereas the twins includes the polysorbates ones. Twins includes the polysorbates. Direct questions, 100% direct questions are asked on this topic. Okay students, so now as you can see, there is a scale that has been drawn right here, which indicates the strength of your surfactant, that can be defined with a HLB scale. Now this HLB scale, I'll just mention here. Yeah, surfactant. So it was introduced by a scientist named Griffin in 1947. This scale actually represents the hydrophilicity and the lipophilicity of the compounds, which includes that if the HLB value is high, which is the hydrophilic lipophilic balance, if the value is high, it will be the hydrophilic one. If the HLB value is low, then it will be the lipophilic one. Okay students, you can see the indication of the HLB values that has been done on this scale, whereby these are categorized into different lipophilic as well as hydrophilic parts. Okay students, there is one more topic that you should know, that how we determine the HLB. Before that, I am making one small table right here where I'll be writing the HLB values different. Okay students, and here will be the examples. I have already mentioned on the right side, if you can see here, but there is one trick to remember those things. You should know that if the HLB value is nearly 1 to 3, these are categorized as the anti-foaming agents. These are categorized as the anti-foaming agents. Here is the mnemonic that is we are going to make. When the value is around 3 to 6, then these are water in oil emulsifiers. These are categorized as water in oil emulsifiers, which also includes spans as well, right? So AW 3 to 6, then it is 7 to 9. In 7 to 9, these are categorized as the wetting agents. These are categorized as the wetting agents. This comes with a sound of aw that we generally write in our language, in our basic social language that we use. So yes, we can call it as aw. From A is the anti-foaming agents, from the W it is the water in oil emulsifiers, from the other W is the wetting agents. Now if the value is around 16, if the value comes out to be around 8 till 16, then these are characterized as the oil in water emulsifying agents, as well as twins are included. Okay students, very important. Now if the values range from 13 to 15, these are categorized as detergents. If it is more than 15, then it comes as a solubilizing agent. Your SLS, your sodium lauryl sulfates, is actually indicated as a solubilizing agent, right students? So the trick can be this ODS. Okay students, from this you can understand A stands for the anti-foaming agent, W stands for the water and oil emulsifier, the wetting agents, the oil in water emulsifiers, the detergents, and the solubilizing agents, which also includes SLS, which is the surface active agent. So this is students the HLB scale. The values in fact determine what kind of nature will it possess. If the values are higher side, they will be hydrophilic. If the values are on lower sides, they will be categorized as lipophilic. Lower down you can see the examples that have already been discussed. I'll just mark the examples where direct questions are asked. That citramide, these are the quaternary ammonium salts, categorized as the cationic surfactant. The spans and the twins, very important students, these are directly asked in your question. The lecithin as an example of non-ionic surfactants. I have marked all the important examples that can be asked from your exam point of view. Okay students, now let's move on to the next part, that is the So now let's move on to the next part, which includes the determination of HLB, right? So there is very simple formula that is used. A lot of questions are asked from this point also. Very simple formula of determination of HLB, that is the summation of hydrophilic group numbers, summation of hydrophilic group number minus summation of lipophilic group numbers plus 7. Direct questions can be asked based on these formulas, so you can just note it down. Another important formula is the HLB is 20, it is 1 minus S by A. This S is nothing but the saponification number. Direct students, very much direct questions are asked. This A stands for the acid value. Okay students, third formula is HLB is determined by the values of E plus P divided by S. This E stands for the percentage weight of oxyethylene chain, and this P stands for the weight percentage of polyhydric alcoholic groups. Very much direct questions are asked, right? So divide by 5, E plus P divided by 5. So next, another one formula, direct questions are asked on the formula HLB is equal to E upon 5. Now this E is the percentage weight of ethylene oxide. Please mark these formulas as very important. You may be asked that out of the following, is there any formula that is incorrect? Is there any formula that has not been asked? Or directly you will be given the values of saponification numbers and the acid values, and direct questions can be asked from this topic. Okay students, here you can see that I have already discussed about the spans and the twins. Direct questions can be asked on this topic, so you should definitely mark these polysorbates and the spans as very important. You can see the twins as the polysorbitan esters including the polyoxyethylene monooleate is the twin 80. These are the polyoxyethylene monopalmitate, that is the twin 60. The monolaureate is the twin 20. Monomyristate is the twin 40. Very important students. But just you need to first know that what are spans and what are twins. Now let's come to our questions. Now before discussing these questions, I am going to discuss one more important topic that can be asked from your exam point of view. We are going to replace this thank you today with a very important, you are going to thank me today for this topic that we are going to talk about now, because a lot of direct questions can be seen from this topic, is the BET equation. BET equation, direct questions students, direct questions can be asked. BET equation. Now BET equation is actually the equation for the adsorption of the gas on the solid surface. Suppose this is a solid surface. Now the adsorption, the surface adsorption of the gas molecules, assuming a multi-layer adsorption. You can see this is the multi-layer adsorption. So BET equation actually takes into the consideration whereby what happens, whereby the adsorption of gas on the solid surface takes place following the multi-layer adsorption. So there are few assumptions that are made for before the BET equation came actually. So the BET actually, what is BET? BET is the name of the scientist that invented this this equation is the Brunner, the Emmett and the Taylor. in 1938. Very important students, mark it as important. These three scientists came together and gave an equation, BET equation, which indicates the how these gases molecules are going to adsorb on the solid surface. So the assumptions that they made include that the solid surface upon which the gas is going to adsorb must be uniform. The solid surface must be uniform. Secondly, the adsorption of gas molecules at one site may not affect the adsorption of gas molecules on the other side. So the adsorption, second assumption is the adsorption of gas molecules on one side does not affect adsorption of gas molecules on the other side. Very clear. Third, multi-layers are formed. I have already mentioned and already shown that multi-layers are actually formed, but you must see only this first layer is actually in contact with the solid surface, rest others are actually in contact with the previous layer gaseous particles. Okay students, so what is this BET equation? Please mark it as important. Direct representation of equation is the P upon V, P naught minus P is equal to 1 upon VMB plus P minus 1 upon VMB to P upon P naught. Direct questions are asked students. Please note that V is actually the total volume of gas that is being absorbed at a pressure P, while P naught is the vapor pressure and Vm is the quantity of the vapors that are absorbed over the surface, while B is a constant. This is another important topic from your exam point of view that we have discussed today. Direct question on the BET equation, the HLBs, the questions can be asked on what are the values of the HLBs. So I hope you must have understood that what are the topics that on which questions are asked directly. So thank you so much for this session. We will be discussing few more topics in coming future from the physical pharmacy, and keep on revising the topics that I have highlighted and told again and again and told you to mark as important. These are actually very important. When you are going to solve the questions, you are able to see that how questions are actually arise from these topics only. So thank you so much.